Alright friends, welcome back. In this video we're going to go ahead and start our chapter 1, which as you can see by the title is going to talk all about equations, inequalities, and mathematical modeling. So by the time we finish chapter 1 we will have gone through all of these sections here, 1.1 through 1.8, and as you can see we're going to touch on everything from solving linear and quadratic equations to doing inequalities, and even going back to complex numbers and discussing those. So let's go ahead and get started here with our 1.1, and that is of course graphs of equations. So in this video we just want to go ahead and give you a general sense for how to go about thinking about graphs of equations, right? What are the key characteristics of graphs that you need to know? And what are some other things that we can be doing to kind of help make more sense of graphs in the future? So let's just go ahead and start with a basic, what is a graph? A graph of an equation, it says here, is the set of all points that are solutions of the equation. Okay, and so you guys have seen this idea plenty of times in your algebra classes. So for example, if we have an example here that says sketch the graph of y equals x squared minus 2 by plotting points, then we could just set up a quick table like this, and the way that we get our y value is we have this formula that deals with x right here. So this says to take your x input and square it and then subtract 2, which is what I have set up for us ready to go right here. And so what we might do is go through and just go ahead and plug in all of these x values real quick, and then the formula will tell us what to do with those x values, and we will get the corresponding y values. So let's go ahead and have a look at what our outputs would be if we have these 5 inputs here, okay? So we can do this mentally. Negative 2 squared is 4, minus 2, that is going to make 2. And then we have negative 1, and then negative 2, and then we would have here negative 1 again, and then finally we would have positive 2 again, okay? And so these are the outputs that are associated with these inputs here, and the way we would typically characterize these is through ordered pairs, and we could just simply go over to the graph and graph these in the usual way, okay? And when we do, you will notice that we will have the general form or shape in this way, okay? And so plotting those 5 points will get us these 5 skeleton points right here, and we can sketch the graph by going ahead and connecting all of these points with a nice smooth curve. And we would see here that this is one of the classic shapes from Algebra 2, which of course is called a parabola, okay? And that makes sense because that certainly came from a quadratic equation. So plotting points, that is one legit way for graphing. But as we go throughout the chapter, one of the things that we might do is uncover some shortcuts for that type of thing, okay? And so some characteristics about graphs. Let's first go ahead and talk about intercepts. So basically what we're talking about here, folks, is where does the path of your graph cross the x-axis and where does it cross the y-axis, okay? And so a couple of different situations that can pop up depending on what the shape of your graph looks like. We could have no intercepts but one y-intercept here, so we could have a path that doesn't touch the x-axis at all. We can have a path that intersects 3 times on the x-axis and 1 time on the y-axis. We could have, you know, of course, all these other options, right? And there are more. But again, just being aware that these are all different things that can occur. Basically, whatever shape you can draw on an xy plane, that can be a relationship between an input and an output. And so wherever we cross the axes, these are very important locations that we need to make sure that we know how to find. Okay, so for example, in this first example here, they already have the path of the graph drawn here for us. And what we just simply need to do is go through and make sure that we're able to make sense out of the coordinates of these points here, right? So for x-intercepts, of course, that's where we cross the x-axis here. And going from the origin, that apparently is going 3 to the left, so that would be a point with coordinates -3, 0. And then, of course, we have the other one where we went to the right 3 from the origin and did not go up any. So that would be the point with coordinates +3, 0. And then finally, we've got this point right here where we cross the y-axis. That is going up 4, but we don't go left or right any. So the coordinates of that would simply be 0, 4. Okay? And one of the finer details about your x and y intercepts is that when you have an x-intercept, your y coordinate is always going to end up being 0. And for your y-intercepts, your x-coordinate is always going to end up being 0. Here in this next example, it says use your graphing calculator to go ahead and determine these x and y intercepts. And so I already have that ready to go here for us to view. Here is the first function that they gave us. I believe that was x squared plus x minus 2. And so depending on the viewing window in your calculator, it'll be easier than other times to go ahead and figure out where you cross the x-axis here. But pretty clearly here, I think we are crossing here at -2, 0 and +1, 0. So we'll go ahead and write those in here really quick. So we have two x-intercepts there, -2, 0 and 1, 0. And then in the graphing calculator, it looks like we are crossing the y-axis at going down 2 units from the origin. So that would be the point with coordinates 0, -2. Okay. Now, if you are using your graphing calculator and you would like to just go back to the standard viewing window here, up at the very top, you have those 5 buttons. Go ahead and click the zoom button in the middle, and then that'll give you a bunch of options for how to zoom in your graph. What we want is this 6th one down here, the one that says zoom standard. If you just press enter on that, then it'll go ahead and reframe your grid and redraw your function. Okay, but let's go ahead and take a look at that next one. I've got the next one here ready to go, so let me go ahead and arrow over to the equal sign and press enter to turn that graph off, and then we'll arrow down to the next equal sign and we'll turn that on because we want to go ahead and graph the function 4 over x plus 1. And so if we graph that, here is what we are looking at right here. Okay, so the thing about this is that this is what you call a rational function, and rational functions have these things called asymptotes, which are boundary lines that your graph is never going to touch or cross. And here it just so happens that the x-axis is one of those asymptotes. It's one of those boundary lines that the path of this graph will never touch or cross. So when we go to the x-intercepts on this, one of the things that we'll say for our next function is that there are really none to speak of. Okay, because the x-axis is an asymptote, we are never going to touch it or cross it, meaning we never have x-intercepts on that graph. Now, y-intercepts, actually, you have this top part crossing here at, it looks like I have to go 4 units up from the origin. So that would be a point with coordinates 0, 4. And as far as in the negative sense, I believe the graph here is just going to keep going and keep going until it reaches negative infinity, which it's kind of counterintuitive to say that it will reach negative infinity. That will never be a thing. So we'll just say that we have that one y-intercept, and we'll move on to the next one. Okay? So I think I accidentally opened my Paint program here, so if that pops up, yep, there it is. We'll exit out of that. Okay, so go back to the calculator here. Let's go ahead and take a look at that next function. So let me turn my second one off by, of course, again, going over the equal sign and pressing enter, and then we'll go ahead and take a look at this very last one. So it looks like we are going to have this characteristic shape right here. It looks like we have an x-intercept at 4, 0 and a y-intercept at 0, 4. So going to the right 4 units from the origin and then going up 4 units from the origin. So we'll go ahead and list those here. So that would be 4, 0 for the x-intercept, and that would be 0, 4 for the y-intercept. So again, you'll notice what all of these x and y-intercepts have in common is that all of the y coordinates are 0 on your x-intercepts, and all of your x coordinates are 0 on your y-intercepts. That will always be a pattern that will follow us whenever we get to talking about intercepts here. Another thing about graphs is that they do have, depending on the function, they do have a good sense of symmetry in their shape. Again, that depends on the function that you're graphing, but there's typically 3 different types of symmetry that you'll see graphs having in the xy plane. We can have symmetry across the x-axis, which basically means that your x-axis here is acting as a mirroring line. And so part of the graph is looking into this mirror right here and seeing its reflection. We could also have functions whose mirroring line is on the y-axis here. So we mirror across that line. And then we also have rotational symmetry, or in other words, origin symmetry, which this is to say that if we were to take the shape of the graph and spin it around a point, then it would have the same shape as if we had spinned it 180 degrees, okay? So typically when you talk about origin symmetry, we are talking about spinning around that origin point, that 0, 0 point. But these are the different types of synergy that we have, and so being able to make some sense out of those symmetries, we can go ahead and look at an example like this. So it says, assume that the graph has the indicated type of symmetry, which the one that they're indicating here for us is y-axis symmetry. We would just need to sketch the complete graph of the equation. So if we have y-axis symmetry, then that means that the mirroring line that part of my graph is looking into to see its reflection is this y-axis right here, of course. And so in order to go ahead and copy that over, one of the things that we may need to go ahead and maintain here is the distance that each point is away from the mirroring line, okay? So if we go ahead and just start kind of plotting some points here on our graph, we might see here that the distance that we have here is just going to be 1 right here, it's going to be 2 right here, it's going to be 3 right here, and so on and so forth. So that would just need to be something that we copy on the other side of the line and plot those points here. So copying these distances, we're going to be able to plot these points. So we have a distance of 2 and 1, and also a distance of 3 there, and plot that point. This gives us a guaranteed way to connect these dots and draw a perfect mirror image on the other side of that line. And that's the deal with symmetry, is that the distance from each point on the graph to the mirroring line is going to be the same on both sides of that mirroring line, or that line of reflection, okay? There are some algebraic ways to test to see if graphs are going to end up being symmetric, and here are the tests right here. So if you want to test to see if your graph has a mirror line on the x-axis, then here's what you will do algebraically with your equation. Everywhere that you see a y, you will take it out and you will replace it with negative y in parentheses. Okay, what you're looking for is to see if anything changes, right? If you end up with the exact same equation after doing that, then that means you're going to have x-axis symmetry. Works similarly if we have y-axis symmetry. We're going to take all the x's that we see in our equation, we're going to replace them with negative x in our equation, and we're going to see if anything changes. If nothing changes at all, then that means we're going to have these symmetries. Okay, so we might make a little bit of a note there. If you end up with the same equation with no changes, okay, so if you end up with the same equation, that's what you're looking for in these tests, okay? And then finally, if you want to test to see if you've got origin rotational symmetry, then you're going to basically do that process, but with both of your variables, x and y, okay? My box got a little bit messed up there, but not going to bother changing it. Again, these are algebraic tests that we can perform to test to see if we have these specific types of symmetry. So let's go ahead and take a look at an example of that. So it says, check this equation, x minus y squared is equal to 0 for symmetry with respect to both axes and the origin, okay? So let's first go ahead and test to see if this has x-axis symmetry, and I have my ink to shape tool on, so that's taking all my letters and making them real weird. Okay, we'll test for x-axis symmetry, y-axis symmetry, and then finally we'll test for origin symmetry, okay? So if we're going to try to test for x-axis symmetry, we're going to take our equation, which is, of course, x minus y squared is equal to 0. And what it said to do on the previous page is we are going to go ahead and, we'll just read it here real quick, we're going to replace every y that we see with negative y in parentheses, and we're going to do the operations and see if anything changes. So I see a y right here. It's basically the thing that I'm squaring in the equation, so we're going to take that y out, and we are going to replace it with negative y. Okay, and the question is, after you simplify, does anything change? Well, basically we're looking right here in our equation, and we are seeing here that that is going to be a negative y in parentheses that's being squared. A negative squared, or a negative times a negative, is always going to end up being positive, and so that's going to mean we're going to end up with x minus y squared is equal to 0, and you will notice that there is really no change from where we started. Okay, so if you're able to plug in negative y, and nothing changes when you simplify, that means that we will have this type of symmetry. So I'll just put a big check mark up here to signify that yes, we do have that type of symmetry. We're going to do that same thing with y-axis symmetry, but now instead of plugging in y, we're going to plug in x. So we're going to start with our equation. We're going to take this x that we see, and we're going to plug in negative x in parentheses, and we're going to see if the operations in our equation put us in a position where we end up where nothing changes. Well, because no operations are really occurring onto that x besides that subtraction, which won't really change the sign of the x, what we end up with here is negative x minus y squared is equal to 0. And you can do some fun, cheeky things here, like factoring the negative out, something like that, and maybe divide both sides by negative 1 so that you end up here with x plus y squared is equal to 0. But that's not what you started with. Okay, so if you take a look at what you started with there, that is going to be something that changed. Okay, so that is going to mean that we do not have y-axis symmetry in this equation. okay? And then the thing about testing for origin symmetry is that we've pretty much already done the work for both, okay? We know, because for origin symmetry we would have to plug in both x and y, which I'll just go ahead and write some spaces for here, okay? We have already tested the plugging in of negative x and the plugging in of negative y, and we know that while this part will work out, we know that the x part will not work out. And so we know automatically that the origin symmetry is not going to be present in this graph, okay? And if you wanted to, you can go ahead and use a graphing calculator and graph this equation and see for yourself that it will definitely have this x-axis symmetry in it, but it will not have the other two. I'll leave that for you guys to do if you like. But let's go ahead and take a look at another example of that. Okay, so here we have a different equation. We have x times y is equal to 4. We want to test for all three types of symmetry. So we have x-axis, we have y-axis, and we have origin. Okay, so let's see what ends up happening here. So for x-axis symmetry, we are going to go ahead and take all the y's that we see in our equation, and we are going to replace them with negative y and see if anything changes. Okay, so when we do that, do we change from the original? Well, yes, because a positive times a negative makes a negative. This is going to end up simplifying to negative xy is equal to 4. And if we simplify, maybe divide both sides by negative 1, we end up here with x times y is equal to negative 4. And that is not the same as what we started with. We wanted x plus y is equal to 4. So because that's not the same as what we started with, we're going to go ahead and say, nope, we don't have x-axis symmetry. Okay? For a similar argument, look at y-axis symmetry, right? Here is where we replace x with negative x and see if anything changes. Okay, well, by similar reasoning here, you would arrive at the exact same conclusion that we just did for x-axis symmetry, where you would see that x times y is equal to negative 4, and that's a problem as well, so no y-axis symmetry in this graph. However, remember that the origin symmetry requires that you test both. So what if we were to start with our original equation here? This is what we want to be the same as when we're all done. And replacing x and y is going to be negative x and negative y, and we're going to see what ends up happening here. Well, you might see where this is going, because a negative times a negative does make a positive, so this is going to end up being x times y is equal to 4, and that is the exact same as what we started with. Okay? And so that means that we do have rotational symmetry on this graph, and so this is the only type of symmetry that this graph will have right there. So again, these are a little bit of a test algebraically to see if the graph is going to end up having the types of symmetries that we're looking for. Speaking of symmetries, circles are probably the most symmetric shape we have in just all of geometry. And there are ways to graph circles in the xy plane through equations. And so the standard form of the equation of a circle is given right here. Okay, this is the general formula for the equation of a circle in the xy plane. And a couple of key items that you will want to make sure to pay attention to here are the following. Okay. First of all, you have your x and y. That's your independent and dependent variables, respectively. But you have this on the the right-hand side of the equation. You have this variable r, and what that is the radius of the circle. So remember that the radius of the circle, if you look at the picture down here, that is just simply the distance from the center of the circle to the circle's edge, and that actually turns out to be a number that shows up in the actual equation for us. So that's pretty good. The other thing that we have here is we have these numbers h and k in the mix, okay? And what those are the coordinates of the center of the circle, okay? So where you'll start off by drawing your circles in the xy plane is you'll start with the actual center and then plot that point, and then you'll use the radius to get to the rest of the circle, okay? The other formula for a circle is just one who specifically has a center at the origin. Remember, that's the coordinates h and k. And so if you were to actually plug in 0 in for h and k up here, you'll notice that x minus 0 and y minus 0, those are just turned into x and y respectively, and we would just end up here with this equation right there. Okay, so we have a special case whenever we have a circle centered at the origin. So if we take a look at this first example, it says find the center and radius of the circle with this equation and then sketch its graph, okay? Well, what we want to do is we want to match this up with the general equation of a circle and then see what is playing the role of what and identify some of our key parts there. So there's the general equation of a circle, and if we go through real quick, I think it's really easy to go ahead and pinpoint what's playing the role of h. That would simply be 2. And if you look at your y term, that just says y squared. So for us, what that means is that playing the role of k is not a 1, it's a 0, okay? And so playing the role of k there would simply just be 0. So what that means for us, remember h and k, that is the coordinates of your center point. Your center point is going to have coordinates h and k, and so for us, playing the role of h is 2, playing the role of k is 0. So that means that your center point is at a point with coordinates 2, 0, so I might just go ahead and plot that point here really quick. Right there, that's the point with coordinates 2, 0, and then the only thing left that we need is the actual radius of the circle. And remember, that's where we are looking at this number here. Now, be careful, because this number that it puts here is 4, but in the general equation, we're looking for r squared. Okay, so one thing that you can do if you wanted to be thorough about it is you could go ahead and say 4 is what they had. I know that that has to be the same thing as r squared, and you could set that equation up and solve, or informally what you could just do is say, well, I need to be able to square this number in order to get 4, and the only number that we can square to get a 4 is, of course, a 2. So just kind of thinking through it mentally like that, we might reason that the radius of our circle is just going to be a 2, okay? So in order to go ahead and draw the rest of the circle, we might hone in on the graph. We know that this is the center. What I might do is I might just go in directions of north, south, east, and west, counting out my radius, plotting those points, and then that would give me a nice skeleton to draw the circle. So I can go 2 to the north, because the radius is 2, 2 to the south, 2 to the east, and 2 to the west, okay? And that gives me a nice skeleton, and I can just go ahead and approximate the rest of what this circle would look like here and do more of a shape like that. And since I have my ink to shape tool on, it's doing its best job to try to go ahead and draw that circle there for me. So something that looks a little bit like that would be what we would want to go ahead and produce for the graph here. Okay, so you can graph circles. Again, they always have that general shape. And so let's go ahead and take a look at another example where that might come up here, right? So example 7, write the standard form of the equation of a circle with a center at 3, -2 and a radius of 3. So just remember that your center is points h and k, your radius is r. So if we start off with the general equation of a circle, that is x minus h squared plus y minus k squared is equal to r squared. All we have to do is just plug in our stuff. So x minus h, playing the role of h today, is positive 3. We'll square that and then add on y minus k. Now, keep in mind here, k is a negative number, so when we subtract it off, this is going to become a plus sign. So we'll say y plus 2, and that is going to be equal to your radius squared. Well, our radius is here being played by 3, so if we were to square that value, that would be squaring 3, and that, of course, would be 9. And so we'll go ahead and leave a 9 there, and this would be the general equation of a circle with that information. Okay, so real straightforward whenever we are just given the information and we are asked to go ahead and apply it into the equation here. And my computer is doing all sorts of weird things today, so let's do our best to kind of move on here. Goodness. All right, so example number 8, write the standard equation of, or standard form of the equation for the circle with endpoints of a diameter at -4, -1, and 4, 1. Okay, so real quick, a diameter in a circle, if I draw a circle here really quick, okay, the diameter, if here is the center, the diameter is just the total length going across the circle and passing through the center. Okay, that's the diameter there. So make a note of that. That is the diameter of your circle. And apparently our diameter is going to have some endpoints for us. It's going to have one endpoint at 4, -1, or sorry, -4, -1, I should say. And then the other endpoint is going to be at 4, 1. So let's actually plot that and see what that looks like. So go to the left 4, down 1. Go to the right 4, up 1. There is going to be our diameter right there. Okay? So what I might do is, you don't have to do this, but I might just go through and put a little bit of a dashed line there to say that that is the diameter of my circle. Well, if you take a look at this real quick, the diameter, of course, passes through the center always. So if you go right in the middle of this dotted line segment that I just drew, we might put ourselves right here. And I know that that would be in the center. You can go ahead and use maybe an argument of slope in order to get there, because for every 1 I go up, I go 4 to the right. And if I were to go up 1 more and 4 more to the right, I would be at my other destination there as well. So I do know that that is going to be the center of my circle. Now, what we need, of course, for the standard equation of a circle, if we write it down here really quickly again, is we need the coordinates of the center. That's h and k. And we need radius. Okay? Well, by doing that whole slope idea, we know that the coordinates of the center here are going to be right there at the origin, 0, 0. So that is what's playing the role of h and k in this example, is 0 and 0. So we know we have that special case from a couple of slides ago, where instead of writing h and k in here, since they're both just 0, we can just say that x squared plus y squared to r squared. Okay, so that's the special case where the origin is going to be the center of our circle. Okay, so I'll say that here. 0, 0 leads us there. Okay, so what this means is that if we know what the radius is now, we could just plug it in, and then we're going to have our equation. Okay, so kind of begs the question, how are we going to find the radius? Well, remember that the radius of the circle is that distance that goes from the center of the circle right to the circle's edge. Okay, and so what we might do is kind of brainstorm a little bit on how we might find this distance right here. Okay, well, again, going back to that slope example, right, what we said before is that for every 4 units I go to the right, I go 1 up. For every 4 units I go to the right, I go 1 up. That's really an argument about steepness, but what I want you to do is I want you to notice what we have basically just drawn here. We've drawn the shape of a triangle, and this is not just any triangle here. This is, of course, a right-angled triangle. Okay, and so one of the things that we might remember from geometry class is something that relates. If we have here them out on the grid, this would be a length of 4 right here, which I'll go ahead and do it in a different color. Right, this would be a length of 4 right here, and this would be a length of 1 right here. What we're looking for is the radius, and so how we might view that is the hypotenuse of this right triangle, and we can go ahead and employ Pythagorean theorem in order to figure that out, right? So Pythagorean theorem said a squared plus b squared equals c squared. Playing the role of a for us is 4. Playing the role of b for us is 1. So if we're doing a squared plus equals c squared, we might do 4 squared plus 1 squared, and that's going to be equal to c squared, which is our radius. And so playing the role of c is just going to be that radius that we wanted, r squared, okay? And so if you clean this up, 4 squared is 1 squared is 1, so that would be 17 is equal to r squared. And so if we take a square root of both sides, the square root of 17 is going to be equal to our radius, okay? And so that means over here, plus y squared is equal to squared. What we can do is replace that r with the value for r that we just found, which is the square root of 17. But I want you to notice what is going to happen here when we do that. Okay, so x squared plus y squared is equal to this squared. If we take the square root of 17 and square it, those are inverse operations and undo each other. So that just simply leaves us with that radicand of 17. And so we arrive at the equation of our circle here. Okay, so x squared plus y squared is equal to 17 will be the equation of a circle with these endpoints of the diameter there. Okay, and if you wanted to, you don't have to, but you could go ahead and do your best approximation of the circle here. I'm going to go ahead and do a very awkward one, but thanks to ink to shape, it turns out to be a little bit better. So that's going to do it for the end of the video. Here's the assignment that goes with this lesson. I hope this video has been of some help to you. If you have any questions, please let me know. But that is all I have for this one. Thank you very much. I will speak to you guys in the next one.